here we continue to look at another example. So in this example, we're considering a system as plotted here with this HLP being an ideal low-pass filter, okay? And let's see what is the effective, input-output relation of these two. Okay. Now this is an ideal low-pass filter with cutoff frequency pi over 4 and a unity gain. Okay. So if you plot this out, it will look something like this. So suppose this is pi over 4. So this spectrum is like this. Okay? With a unity gain. So this is 1. All right? Now in discrete time, this should repeat itself every 2 pi. Okay? So you have one at 0 frequency, but you should also have one at 2 pi, 4 pi, and so on and so forth. Okay. So you should also have one here. And one here. Okay, so on and so forth. Okay. All right. Now let's look separately at what happens in the upper branch and the lower branch. Okay, and then we combine them together later on. So in the upper branch, we start by passing xn, multiplying it with -1 to the power n. Okay. Now notice that -1 to the power n you can actually view as e to the j pi n. Okay? And this is because -1 is actually e to the j pi, right? So when you take -1 to the power n, this is actually e to the j pi n. All right. So the reason, 我们还没讲到这个，对，这个是等一下会讲到，先不要看这个，对。所以这个是 HLP 啊，这个是 H， 等一下会告诉你。OK。Okay. So anyway, this is the answer that we will get. Okay. So this is the effective frequency response of this entire thing. Okay. And we're trying to show that this is indeed the case, right? Okay. So we start out by passing xn through the upper branch. We first multiply it by e to the j pi n. So the reason it's convenient to look at this instead of -1 to the power n is because when we multiply a signal by this phase shift, then in the frequency domain, it will correspond to a frequency shift of pi. Okay? So this w1n, which is e to the j pi n xn, okay? So this thing, right, in the frequency domain, W1 e to the j omega is x e to the j omega minus pi. Okay? So because of this, right, the spectrum that you get here is equal to the spectrum of x shifted by pi. Okay. And then when we pass through a linear time invariant system with impulse response, with frequency response HLP, this means that the output spectrum which is the spectrum of W2. All right, so then the spectrum of W2 should be equal to the frequency response times the input W1, which is x e to the j omega minus pi. Okay? So W2 is this thing here, okay? So the spectrum at the output of this subsystem is equal to the input spectrum times the frequency response. And the input spectrum is this frequency shifted x, okay? So we have this frequency shifted x times the frequency response to get the spectrum of W2. Okay. All right. Now, if you multiply W2 by -1 to the power n to get W3, then similar to what you get here, W3 should have a spectrum that is a frequency-shifted version of the spectrum of W2. Okay? So also, we know that W3n, if you write it as e to the j pi n times W2n, then in the frequency domain, W3 e to the j omega, okay, should be a frequency-shifted version of W2. Okay? And W2 looks like this. Okay? So I just substitute this inside here. But be careful, instead of omega, I should have omega minus pi. So insert it inside here and here. Okay. So this becomes HLP e to the j omega minus pi x e to the j omega minus 2 pi. Okay? Now, the discrete time spectrum is periodic with period 2 pi. So minus 2 pi, right, has no effect on this, right? So I can, this omega minus 2 pi is actually equal to the spectrum at omega. So this becomes HLP e to the j omega minus pi x e to the j omega. Okay? All right. So this is the upper branch. Right? If I plug in x into this upper branch, I will get at the output of the upper branch W3 that has a spectrum equal to this. Okay? Now, for the lower branch, it's much simpler. Right? It's simply the spectrum of x times this low-pass filter. So W4 e to the j omega is just HLP e to the j omega. I'm sorry, there's no minus here. Okay. Okay. So anyway, in the lower branch, this should be HLP times x e to the j omega. Okay. So then the output of the entire system is just the sum of W3 and W4. So hence, y e to the j omega, which is W3 plus W4. Okay. So if I plug both of these inside, okay, I will get HLP e to the j omega minus pi plus HLP e to the j omega times x. Okay. So by the convolution property, you may immediately see that this thing inside the bracket is the effective frequency response of this system between x and y. Okay? So this thing here is the effective frequency response. Okay? And what does this effective frequency response look like? I have this low-pass filter, right, which takes on this rectangular shape at around 0 frequency. And then I have this low-pass filter shifted by pi. Okay? So I should also have this shifted to pi. Okay? So if you combine these two, I should end up with a spectrum like this, where you have a passband both at 0 frequency and both around pi and minus pi. Okay? So the effective response of this system gives you a system that passes through both low and high frequency, or in other words, it suppresses these intermediate frequency components. Okay? Okay, any questions here? Okay. So, this outcome, right, going over this seems rather straightforward, right? But if you think about it, suppose you are not aware of the convolution property, and you're asked to find what is the impulse response between the input and output here. So you can see that it's much more difficult if you do this in the time domain. Okay? So you would have to multiply by this, take a convolution with some sinc-like function, multiply again by this. This is much more difficult to deal with compared to this frequency domain approach. Okay? So first of all, it's much easier, mathematically to make this derivation. And secondly, it also gives you more insight, right? Because looking at the frequency domain response, you can see what is really happening in the system. The system, you can see that the system passes through low and high frequency components and suppresses intermediate components. Now, this is more difficult to see just by looking at the impulse response. Okay? Okay. All right, so this is the convolution property. So convolution property says that if you have convolution in time, then you have multiplication in frequency domain. Okay. So it also holds the other way around, which gives you the multiplication property. Okay. So multiplication property says that if you have multiplication of two signals in the time domain, then this corresponds to convolution in the frequency domain scaled by 2 pi. Okay. But you have to be careful here because what you have here is actually what we call a periodic convolution because you're performing this convolution only over a range of 2 pi. Okay? All right, so this is what we call a periodic convolution. Okay? Right. So we can show this using the same approach as before. Okay? So suppose you just start out by writing the formula for the Fourier transform. So this y spectrum should be equal to summation yn e to the minus j omega n from minus infinity to infinity. Okay? And yn is the multiplication of x1 and x2. So if you replace with that, you get summation x1 times x2 e to the minus j omega n from minus infinity to infinity. Okay. Now, the next step that we do is to replace this replace this x1 with its inverse Fourier transform formula. Okay. So instead of writing x1, we write 1 over 2 pi, the integral of x e to the j theta e to the j theta n d theta x2n e to the minus j omega n. Okay? So I'm replacing, this should be capital X1. Okay? So I'm replacing this time domain, lowercase x1n, with this inverse Fourier transform formula. Okay? And then we just sort of interchange this integral and the summation, right? So we bring this integral outside. So this will give us 1 over 2 pi integral x1 e to the j theta summation x2n e to the minus j omega minus theta n d theta. Okay? So I'm bringing out this 1 over 2 pi integral x1 right over here, bringing this summation inside so that I have a summation over x2, and then combining these two terms, I get e to the minus j omega minus theta times n, okay, d theta. All right. Now, if you look at this summation here, this is exactly the form of a Fourier transform of x2 at frequency omega minus theta. Okay. So this term here is exactly x2 e to the j omega minus theta. Okay? So if you plug that in, we get the result that we want, which is integral 1 over 2 pi integral x1 e to the j theta x2 e to the j omega minus theta. Okay? So this is the result that we want. Okay. All right, so let's look at an example for this. Okay. So I want to emphasize that here, instead of having a convolution with the integral going from minus infinity to infinity, we now actually have a convolution only over a period 2 pi. Okay? And here, the spectrum of both x1 and x2 are both periodic, right? Because these two are discrete time signals. Therefore, both of these spectrums are periodic. Okay? Now, when you want to take the convolution of two periodic signals, conceptually, it can be a little bit confusing because convolution is sliding one signal through the other signal, right? But since you have a periodic signal, even though, as you slide the signal over, even though, as the signal leaves the previous signal, you may have another replica of it coming in, okay? So you have to be a little bit careful when you do this convolution. Okay. All right. So here we're looking at example where x1, both x1 and x2 are sinc-like functions, and they actually correspond to rectangular spectrums, right? One, okay. So I'm not plotting out x1. Okay, so for x1, you should have a spectrum going from minus pi over 2 to pi over 2, right? This rectangular spectrum. But it should repeat every integer multiple of 2 pi, okay? And similarly for x2, x2 is actually given here. You have this rectangular spectrum going from minus 3 pi over 4 to 3 pi over 4, and it repeats every 2 pi. Okay. So what is this x1 hat here? Right? x1 hat is just one period of the spectrum of x1. Okay, and we'll see in a moment why we want to look at this. All right? But just keep in mind right now that the spectrum of x1 is periodic. Right? You should have this repeated every 2 pi. Okay. All right, so how do you find the spectrum for x1 times x2? So by the multiplication property, we know that the spectrum is the convolution of the spectrum of x1 and the spectrum of x2. So this is 1 over 2 pi. Suppose we integrate from minus pi to pi, x1 e to the j theta, x2 e to the j omega minus theta d theta. Okay. So like I mentioned before, x1 is periodic, right? It should repeat every integer multiple of 2 pi. But since we're integrating only over one period of this theta, right, from minus pi to pi, so we can actually just limit ourselves to looking at a single period. So I can actually replace x1 with this x1 hat. Okay? So instead of looking at x1, I can now look at x1 hat. Now, since x1 hat has 0 outside of this period, minus pi to pi, therefore, I can extend this integral from minus infinity to infinity. Okay? So I can write this as 1 over 2 pi integral extended to infinity by replacing x1 with x1 hat times x2 e to the j omega minus theta d theta. Okay? And the advantage of doing this is that now, we don't have to worry about these replicas when we slide the two signals over each other. okay? So now what we have here is a more conventional convolution rather than the periodic convolution, okay? So we're more familiar, right? Our insight is more consistent with this type of convolution, okay? And even more, right? So if you write it in this form, you're actually sliding x2, right, over x1 hat, okay? So you have to take this periodic signal, you have to flip it around, and then slide it through x1 hat. But this can be very confusing because all of these replicas that you need to deal with, okay? But actually, by this conventional convolution formula, you know that you can flip this around without changing anything, right? So you can actually instead write this as 1 over 2 pi x1 hat e to the j omega minus theta x2 e to the j theta d theta. Okay? So by this conventional convolution, it doesn't really matter whether you slide x2 through x1 hat or if you slide x1 hat through x2, okay? Now, it's actually easier to visualize if you slide x1 hat through x2, right? So x1 hat is not periodic. It's easy to see what it looks like when flipped around and slid through this x2. Okay, because you don't have to deal with these replicas that may come in, every 2 pi. All right? So this is just a small trick to help you compute this periodic convolution, right? By just first taking just one period of one of these signals, okay? You can take one period of one of these signals and slide it through the other periodic signal, okay? And this is the result that you will get. So the insight here is to slide a period of x1 through x2. Okay? All right. Okay, so this is about all, most of the properties that I wanted to talk about, which we have also looked at in the continuous time case. And actually, a lot of these properties also hold when we were talking about Fourier series representation. Okay, so if you want to look at some other properties that we didn't really talk about in detail, right, it's summarized in these tables in the textbook, okay? So we looked at several of them, such as linearity, time shifting, frequency shifting, conjugation, time reversal, time expansion, so on and so forth, okay? So I think we've covered, a big chunk of these, okay? Right, and this is just some common Fourier transform pairs that you can use.